They built a plane so fast, so secret, and so impossibly advanced that 50 years later, engineers still struggle to fully explain how it worked. A machine that flew at the edge of space, outran every missile ever fired at it, and was made from a metal so difficult to work with that the factory workers had to learn entirely new ways to think about building aircraft. A plane that the CIA funded, Lockheed built in secret, and the Air Force flew into history. This is the story of the State Route 71 Blackbird, the fastest air-breathing aircraft ever to leave the ground, and the almost unbelievable human story of how a small group of obsessed engineers, test pilots, and spies created something that the laws of physics should have said was impossible. Before we go any further, I want you to think about something. Right now, as you sit there, the fastest commercial airplane you could fly on moves at roughly 570 miles per hour. That is fast enough to cross the continental United States in about 5 hours. Now imagine an aircraft that flies at 3 times the speed of sound. An aircraft moving so fast that the friction from the air alone heats its skin to temperatures exceeding 500 degrees Fahrenheit. An aircraft so fast that if you fired a surface-to-air missile at it from directly below, the pilot's only required maneuver was to push the throttles forward and simply fly away from the missile. Not dodge it, not deploy countermeasures. Just fly faster than the missile could follow. That was the State Route 71 Blackbird. That was the Habu. And the story of how it came to exist is one of the most extraordinary tales in the entire history of human engineering. We are going back to the late 1950s. The Cold War is at its most dangerous and most paranoid moment. The United States and the Soviet Union are locked in a contest that neither side fully understands. And the single most dangerous gap in American intelligence is this. Nobody in Washington knows exactly what the Soviets have. Nobody knows how many missiles they have, how many bombers they have, where their military installations are located, or what their true capabilities might be. This ignorance is terrifying because in the nuclear age, ignorance can mean annihilation. President Eisenhower understands this. His intelligence advisors understand this. And so, in the deepest secrecy, an extraordinary program begins. The answer, at first, seems simple enough. Build a reconnaissance aircraft. Send it over Soviet territory at very high altitude, so high that Soviet fighters cannot reach it, and photograph everything. That aircraft becomes the Lockheed U-2, a strange, elegant, almost fragile-looking glider powered by a jet engine, capable of flying above 70,000 feet. And for a while, it works perfectly. The U-2 flies over Soviet territory, photographs missile sites, bomber bases, and military installations, and returns home safely. Eisenhower is briefed. The intelligence gap begins to close. Everyone in Washington breathes a little easier. And then, on the first day of May, 1960, a Soviet surface-to-air missile does what everyone had assumed was impossible. It reaches up and touches France's Gary Powers and his U-2, and the whole program comes crashing down, literally and politically. Powers survives the shoot-down. He is captured, put on trial in Moscow, and the entire secret program is exposed to the world. Eisenhower is humiliated. The intelligence community is thrown into crisis. And the question that now burns in every mind in Washington is this. What do we do now? How do we keep watching the Soviets when they can now shoot down our best reconnaissance aircraft? The answer to that question is already being worked on, in a building so secret that most people in the American government do not even know it exists. It is called the Skunk Works, and it is the most extraordinary engineering organization in American history. Located in Burbank, California, inside the Lockheed Aircraft Company, the Skunk Works was established during World War II under a brilliant, difficult, visionary engineer named Clarence Leonard Johnson. Everyone called him Kelly. Kelly Johnson had a philosophy that was almost militantly simple. Put your best people in a small room. Give them absolute freedom from bureaucracy. give them impossible problems to solve, and then get out of their way. It sounds simple. In practice, it produced miracles. Kelly Johnson had already created the U-2. He had already pushed the boundaries of what was aerodynamically possible further than anyone had ever thought to push them. But now, with the U-2 program compromised, Kelly Johnson sits down with a blank sheet of paper and asks himself the question that will consume the next several years of his life and the lives of everyone who works for him. How do you build an airplane that cannot be shot down? Not an airplane that is hard to shoot down. Not an airplane with better countermeasures or better evasive maneuvers. An airplane that is, in any practical sense, untouchable. An airplane that flies so high and so fast that no missile in existence, and no missile that could realistically be built, could ever catch it. The answer Kelly Johnson arrives at is both elegant and terrifying in its audacity. You build an airplane that cruises at Mach 3, 3 times the speed of sound, at altitudes above 80,000 feet. At that speed and that altitude, the aircraft is essentially immune. Missiles of that era simply do not have the performance to intercept something moving that fast, that high. The aircraft would cross the entire Soviet Union from border to border in less than an hour. It would photograph everything below with cameras so powerful they could read a newspaper headline from 80,000 feet. And then it would be gone before anyone could do anything about it. This was the vision. Now came the problem. Actually building such a machine was not an engineering challenge. It was not even a very difficult engineering challenge. It was, by any reasonable measure, completely impossible. And Kelly Johnson and the Skunk Works were going to do it anyway. The first problem was the material. When you fly at Mach 3, the air friction heats your aircraft to extraordinary temperatures. The leading edges of the wings, the nose, the engine inlets. All of these surfaces are exposed to temperatures that would soften and destroy conventional aluminum, the material from which virtually all aircraft of that era were built. Aluminum begins to lose its structural integrity at temperatures that Mach 3 flight generates routinely. So aluminum was out. The engineers needed a different material. They needed something that was strong, light, and capable of withstanding temperatures of over 500 degrees Fahrenheit for extended periods of time. They needed titanium. Now, titanium is a remarkable metal. It is stronger than steel at a fraction of the weight. It retains its structural properties at very high temperatures. It is, in almost every measurable way, the perfect material for a Mach 3 aircraft. There is only one problem with titanium. And it is a problem so severe that in the late 1950s, almost no one in the American aerospace industry knows how to work with it. Titanium is extraordinarily difficult to machine, to weld, and to fabricate. The tools that work perfectly on aluminum shatter or wear out almost instantly when used on titanium. Standard welding techniques produce welds that are brittle and unreliable. The metal behaves in ways that seem almost deliberately perverse. It reacts to common cutting fluids. It warps unpredictably during machining. It work hardens in ways that make it almost impossible to drill. The Skunk Works engineers had to essentially invent an entirely new manufacturing technology from scratch. They had to learn, through years of patient, expensive, often maddening trial and error, how to work with a metal that seemed not to want to be worked with. And the scale of the titanium requirement was staggering. 93% of the structural weight of the state, Route 71 Blackbird, would be titanium. This was not a titanium-accented aircraft. This was a titanium aircraft. The entire airframe, the fuselage, the wings, the control surfaces, the engine nacelles, virtually all of it was titanium. And in the late 1950s and early 1960s, the United States did not produce enough titanium to build this program. There was a supply problem, and the supply problem had a solution that is one of the most extraordinary ironies in the entire history of the Cold War. The primary source of high-grade titanium, or in the world, at that time, was the Soviet Union. The CIA, operating through a network of front companies and cutout organizations so elaborate that even the people involved sometimes lost track of who was really paying for what. Secretly purchased Soviet titanium, had it processed and refined, and shipped it to Burbank, California, where Lockheed engineers used it to build a spy plane whose entire purpose was to conduct surveillance of the Soviet Union. The Soviets, in other words, unknowingly supplied the raw material for the aircraft that would spy on them. If this were fiction, an editor would reject it as too improbable. The titanium problem was solved. But it was only the first of dozens of seemingly insurmountable challenges that the Skunk Works team had to overcome. The next problem was the engines. An aircraft flying at Mach 3 at 80,000 feet needs propulsion that has never existed before. The engines must produce enormous thrust across an extraordinary range of speeds and altitudes. They must operate reliably in conditions of extreme heat and extreme cold. The inlet air temperature at Mach 3 is ferociously hot, while the atmosphere at 80,000 feet is bitterly cold, and the engines must handle both simultaneously. Pratt & Whitney, one of America's great engine manufacturers, was given the contract to develop the engines, which would become the J-58. And the J-58 is not just an extraordinary engine. It is, in the opinion of many aerospace engineers, the most technically sophisticated air-breathing engine ever built. What makes the J-58 so remarkable is that it is essentially two engines in one. At lower speeds, it operates as a conventional turbojet. But at high Mach numbers, the engine's bypass system partially converts it into a ramjet, a type of engine with no moving parts that uses the ram effect of supersonic air compression to generate thrust. This combined cycle operation, turbojet and ramjet working together in a system of almost unimaginable complexity, is what allows the J-58 to push the State Route 71 to Mach 3 and beyond. Managing the inlet air, slowing supersonic air down to subsonic speeds inside the engine inlet using a movable spike called the inlet cone, is itself a computational and mechanical achievement that required years of development and testing. And the fuel. Standard jet fuel would not work. At the temperatures generated by Mach 3 flight, conventional JP-4 jet fuel would simply boil and vaporize before it reached the combustion chamber. The State Route 71 required a specially developed fuel called JP-7, a fuel so stable and so resistant to vaporization that it was extremely difficult to ignite under normal conditions. In fact, JP-7 is so stable that you cannot ignite it with a match or a spark under most circumstances. The J-58 engine required a special chemical ignition system using a substance called triethylborane, a compound that ignites spontaneously on contact with air, to start the combustion process each time the engines were started. This is a fuel that is deliberately designed to be almost impossible to set on fire, powering engines that burn it in quantities measured in tens of thousands of pounds per hour. The fuel served another purpose beyond propulsion. Because the skin of the State Route 71 gets so hot during high Mach flight, the aircraft needed a way to manage that heat. The JP-7 fuel, circulating through passages in the aircraft structure, served as a heat sink, absorbing heat from the airframe and from the engine systems before being burned. The fuel that reached the combustion chamber was significantly warmer than the fuel that left the tanks. The aircraft was, in a sense, using its own propellant as a cooling medium. Now let us talk about the shape, because the shape of the State Route 71 Blackbird is not merely beautiful, though it is, undeniably, one of the most beautiful machines ever built by human hands. The shape of the State Route 71 is a direct consequence of the physics of Mach 3 flight, worked out through years of wind tunnel testing, mathematical analysis, and the extraordinary intuitive engineering genius of Kelly Johnson and his team. The aircraft is long and narrow, with a needle-sharp nose and a fuselage that blends almost organically into the engine nacelles. The delta wings are swept at extreme angles. The twin tails are canted inward. Every curve, every angle, every surface has been calculated to minimize drag, manage heat buildup, and maintain stability at speeds that no aircraft had ever sustained. There is another aspect of the SR-71 shape that deserves special attention, and it connects this aircraft to a technology that would later become enormously important: stealth. The Blackbird was not designed primarily as a stealth aircraft. Its main defense was speed. But the designers at the Skunk Works, working with radar physicist Edward Lovick, incorporated features into the aircraft's shape and surface treatments that significantly reduced its radar cross-section. The chins, the sharp edges running along the sides of the fuselage, were specifically shaped to deflect radar energy. The aircraft incorporated ferrite-based radar-absorbing materials in certain surfaces. The overall radar signature of the SR-71, while far larger than a modern stealth aircraft, was significantly smaller than a conventional aircraft of its size. The Blackbird was, in a sense, a transitional aircraft, the first machine in history where stealth was a design consideration, even if not the primary one. The color of the aircraft is another story that deserves telling. The SR-71 is black. Not dark gray. Not dark blue. Black. And the reason it is black is both practical and counterintuitive. At the temperatures generated by Mach 3 flight, an aircraft needs to radiate heat as efficiently as possible. Black surfaces radiate heat far more effectively than any other color. So the Blackbird is painted black not to make it harder to see, though this helps operationally, but to help it stay cool. The black iron ferrite paint, applied over the titanium skin, serves simultaneously as a heat radiator, a radar absorber, and a visual camouflage for high-altitude, night-capable operations. It is a solution that solves multiple problems with a single stroke, which is the very essence of the Kelly-Johnson engineering philosophy. The cockpit of the SR-71 deserves its own meditation. The crew of two, pilot in the front, reconnaissance systems officer in the rear, sit in what amounts to individual pressure suits and individual pressure capsules, because if the aircraft were to lose cabin pressure at 80,000 feet, the crew would be dead within seconds. The pressure suits worn by SR-71 crews are essentially personal spacecraft, full pressure suits not unlike those worn by NASA astronauts, complete with their own life support systems. The pilots and RSOs of the SR-71 did not merely fly an aircraft. They wore their aircraft, in a sense. They were as much a part of the machine as any system or component. And flying this machine, actually getting into that cockpit and pushing those throttles forward, was an experience that every pilot who ever did it describes with the same combination of technical precision and barely suppressed awe. The takeoff itself is unremarkable by the standards of high-performance jets. The SR-71 lifts off at relatively modest speeds, its enormous delta wings providing ample lift. But then the pilot begins the acceleration sequence. The aircraft climbs. The speed builds. The Mach meter begins to move. Past Mach 1. Past Mach 2. And then, as the aircraft approaches Mach 3 and the pilots throttle back to cruise settings, something extraordinary happens. The aircraft settles. The ride smooths out. The noise and vibration that marked the acceleration phase diminish, and the SR-71 finds its element, that narrow band of speed and altitude where it was always meant to be, where physics and engineering and human ambition have combined to create something that seems to belong to a different future than the one that produced it. At cruise altitude, the crew can see the curvature of the Earth. The sky above them shades from deep blue to the absolute black of space. Below, the world scrolls past at a pace that the mind can barely process. A mile every 1.7 seconds. The cameras in the belly of the aircraft photograph swaths of territory 80 miles wide and 100,000 square miles per hour of flight. In a single operational mission, The State Route 71 could photograph more territory than an entire fleet of conventional reconnaissance aircraft could cover in days. The name Habu came from the pilots and crews stationed at Kadena Air Base on the island of Okinawa, Japan, one of the primary State Route 71 operating locations. The Habu is a highly venomous pit viper native to Okinawa, a snake that locals regard with a mixture of respect and fear. The Okinawan locals, watching the black SR-71s come and go from Kadena, began calling the aircraft Habu, and the name stuck. The crews embraced it. There was something fitting about it. The Habu is a predator that moves with silent, lethal speed, that strikes before its target can react, that inspires both dread and admiration. It was, the crews felt, a perfect metaphor for their aircraft. The operational history of the State Route 71 is a collection of achievements so extraordinary that listing them begins to feel almost numbing. During the aircraft's operational life, spanning from 1966 to 1990 and again briefly in the 1990s, the State Route 71 flew over some of the most dangerous airspace on Earth. It flew over North Vietnam during the war, photographing surface-to-air missile sites and North Vietnamese military installations at Mach 3, so fast that by the time the Vietnamese radar operators had even registered its presence, it was already gone. It flew along the borders of the Soviet Union, photographing everything that its cameras could reach. It flew over the Middle East during the 1973 Yom Kippur War, providing real-time intelligence to American decision-makers. It flew through international crises and regional conflicts, always bringing back the intelligence that decision-makers needed, always operating just at the edge of what was physically possible. And all through this extraordinary operational history, it was never shot down. Not once. Not by a missile, not by a fighter, not by any weapons system that any hostile nation ever deployed against it. Over the entire operational life of the State Route 71, hostile nations fired more than 4,000 surface-to-air missiles at Blackbirds. Every single one of them missed. The standard evasion technique was exactly as described. The pilot simply pushed the throttles forward. Speed was the armor. Speed was the countermeasure. Speed was the survival mechanism. No nation on Earth ever built anything capable of catching a Blackbird in level flight at operational altitude and speed. There were, however, accidents. The State Route 71 was not invincible against its own complexity. Over the course of the program, 12 of the 32 aircraft built were lost, not to enemy action, but to the brutal demands of operating at the absolute limits of what was mechanically possible. Engine unstarts, events in which the delicate balance of airflow through the inlet system was disrupted, causing one or both engines to lose power simultaneously, were among the most dangerous hazards. An unstart at Mach 3 could subject the aircraft and its crew to forces violent enough to incapacitate a pilot before he could respond. The State Route 71 demanded not just extraordinary skill, but extraordinary physical and mental resilience from its crews, and it tested both without mercy. The pilots who flew the State Route 71 were among the most carefully selected and intensively trained aviators in any Air Force anywhere in the world. They were chosen from the very top of the Air Force's pilot corps, experienced, mature, technically sophisticated, and possessed of a particular kind of temperament that combined coolness under extreme pressure with genuine intellectual curiosity about the machine they were flying. Flying the State Route 71 was not like flying other airplanes. It required understanding the aircraft at a level of technical depth that was unusual even by the standards of high-performance military aviation. The crew spent hundreds of hours studying the aircraft's systems, its limitations, its tendencies, and its failure modes. They flew extensive simulator training before they ever got near the actual aircraft. And even after all of that preparation, the first time a new pilot pushed a real State Route 71 past Mach 2.5 and felt the aircraft begin to really fly, It was an experience that most of them described as unlike anything they had ever encountered. One of the most remarkable aspects of the State Route 71 program is how comprehensively it demonstrated the power of small, focused, liberated engineering teams. The Skunk Works, at its peak for the State Route 71 program, employed a few thousand people. By contrast, the programs that produced contemporary military aircraft of less revolutionary design often employed tens of thousands of people, cost multiples more, and took far longer. Kelly Johnson's management philosophy, which he codified in a set of 14 rules known as the Skunk Works Management Rules, or sometimes just Kelly's Rules, created an environment in which brilliant people could do their best work without being strangled by bureaucracy, committee meetings, or the institutional risk aversion that tends to produce mediocre outcomes. Kelly's rules were simple, practical, and almost radically anti-bureaucratic. The program manager must be given complete control over the project. The number of people with access to the program must be strictly limited. A strong but small project office must be used. The customer must be represented in the project office. Reports must be limited, because too much paperwork paralyzes the creative process. Progress must be measured by results, not by process. These rules sound obvious. They are not. They are, in fact, deeply contrary to the way most large organizations actually function. And they produced the State Route 71. The aircraft was also a commercial and technological gift to the United States that extended far beyond its intelligence-gathering mission. The materials science developed for the State Route 71, the titanium machining techniques, the high-temperature coatings, the specialized alloys, found their way into commercial and industrial applications across the American economy. The computational fluid dynamics work done for the Blackbird's inlet design advanced the entire field of aerodynamics. The pressure suit technology developed for State Route 71 crews contributed to the development of suits for NASA astronauts. The fuel management systems, the hydraulic systems, the electrical systems, all of these pushed the state-of-the-art forward in ways that benefited industries and applications far removed from military aviation. And then there is the record. On July 28, 1976, State Route 71 serial number 17958, piloted by Captain Robert Helt and Major Larry Elliott, set a world altitude record of 85,068.997 feet. On the same day, a different Blackbird set an absolute speed record of 2,193.167 miles per hour, roughly Mach 3.3, over a straight course. These records stand to this day. No production aircraft has ever flown faster or higher. No production aircraft has come particularly close. The SR-71's records are not aging records that will eventually be broken as technology advances. They are records that stand because no one, in the 50 years since they were set, has had sufficient reason to build something to break them, because building something to break them would require an effort comparable to the one that built the State Route 71 in the first place. The retirement of the State Route 71 in 1990 was, to everyone who had any connection to the program, a deeply painful moment. The official justification was cost. The State Route 71 was expensive to operate, requiring enormous amounts of specialized fuel, specialized maintenance expertise, specialized ground support equipment, and specialized crews. The rise of reconnaissance satellites, which could photograph Soviet territory continuously without the diplomatic risks or operational costs of overflights, had reduced the strategic necessity of the aircraft. And so, on January 26, 1990, the United States Air Force officially retired the State Route 71 Blackbird from operational service. The aircraft did not go quietly. Several Blackbirds were retained by NASA for flight research, and they continued to fly into the 1990s, contributing to research programs in aerodynamics, atmospheric science, and sonic boom mitigation. 2 aircraft were briefly returned to Air Force service between 1995 and 1998, when Congress restored funding following concerns that satellite reconnaissance was not providing adequate real-time tactical intelligence. And then, finally, in 1998, the last operational State Route 71 made its last flight, and the Habu returned to Earth for the last time. The machines themselves survive, scattered across the country in air and space museums, on pedestals outside Air Force bases, in the collections of the Smithsonian Institution. The most famous of them, the aircraft that set the speed and altitude records, the aircraft that flew the last operational mission, sit today in carefully climate-controlled display spaces, their black skins still gleaming, their lines still suggesting a speed that the surrounding air has no idea how to handle. Looking at a preserved State Route 71, you feel what you feel looking at any supreme achievement of human ingenuity, a mixture of pride and humility, a sense that whatever else may be said about the species that built this thing, we are, at least sometimes, capable of reaching beyond ourselves. The legacy of the State Route 71 Blackbird is impossible to fully measure. In pure military terms, the aircraft provided intelligence that shaped American strategic thinking throughout some of the most dangerous decades of the Cold War. The images brought back by Blackbird cameras informed decisions made in the White House, the Pentagon, and the CIA, decisions about nuclear strategy, about conventional force deployments, about arms control negotiations, about the real versus imagined capabilities of potential adversaries. The State Route 71 did not win the Cold War, but it contributed enormously to the American understanding of the threat environment that made winning the Cold War possible. In engineering terms, the State Route 71 represents something rarer, a genuine leap. Not an incremental improvement on what came before, but a categorical step into territory that had never been explored. The aircraft flew faster than any air-breathing aircraft had ever flown, higher than any production aircraft had ever sustained, and it did so routinely, operationally, for 24 years. The engineering knowledge embedded in the State Route 71, in its materials, its propulsion system, its aerodynamic design, its systems architecture, represents a concentrated deposit of human ingenuity that has no real parallel in the history of aviation. And in human terms, the State Route 71 is a story about what small groups of extraordinary people can achieve when they are freed from the limitations that most organizations place on creativity and ambition. The Skunk Works at its height was not a large organization. It was not a richly resourced organization by the standards of major defense programs. It was a collection of extraordinarily talented individuals who were given an impossible problem, absolute freedom to pursue it, and a leader, Kelly Johnson, who understood that the best way to get impossible results was to hire the best people, protect them from bureaucracy, and trust them to do the work. Kelly Johnson himself, who died in 1990 at the age of 80, lived just long enough to see his greatest creation retired. What he thought about that retirement, about watching the aircraft he had spent years of his life creating and refining being sent to museums, has been recorded in fragments of interviews and personal writings that convey the precise combination of pride and regret that you might expect from a man who understood, better than almost anyone, what had been achieved and what was being given up. The crews, the pilots and reconnaissance systems officers who flew the Habu, have spent the decades since retirement writing memoirs, attending reunions, and answering the questions of aerospace enthusiasts, historians, and journalists. Their accounts have a consistency that speaks to the genuineness of the experience. Almost all of them describe the State Route 71 not simply as an aircraft, but as a privilege, something that they were extraordinarily lucky to have been part of, something that they knew, even while they were doing it, was unlike anything that had been done before or was likely to be done again. Many of them describe a kind of grief at the retirement that they recognize as disproportionate but cannot suppress. You do not simply fly a machine like the State Route 71. You become, in some important sense, part of it. There is a moment that several State Route 71 pilots have described in remarkably similar terms. You are at cruise altitude, somewhere above 80,000 feet, moving at Mach 3.2. Below you, the world is a curved blue and brown abstraction. Above you, the sky is the absolute black of space. Your pressure suit is doing its job. Your systems are all in the green, and for a moment, just a moment, you become aware that you are, at this precise instant, the fastest human being on the surface of the Earth. Faster than any fighter pilot. Faster than any missile in level flight. Faster than any satellite in low orbit. Faster than anything. Just you and this extraordinary black machine and the thin edge between sky and space. And in that moment, several pilots have reported feeling something that they struggle to articulate. A combination of profound solitude and profound belonging, as though they are simultaneously absolutely alone and absolutely part of something enormous. That feeling, that particular mixture of technical achievement and almost mystical experience, is perhaps the most human part of the State Route 71 story. Because the State Route 71 is not ultimately a story about metal and fuel and aerodynamics, though it is certainly those things. It is a story about human ambition, about the refusal to accept that something cannot be done simply because no one has done it yet. It is a story about Kelly Johnson and his stubborn, brilliant engineers in Burbank. It is a story about the test pilots who first took this impossible machine into the air and learned, flight by flight, how to coax it to its full performance. It is a story about the operational crews who flew it into the most dangerous airspace on Earth and came home safely, every time, because the machine they were flying was fast enough to make them safe. And it is a story about the adversaries who watched it pass overhead, who fired their missiles and watched them fall short, who scrambled their fighters and watched them fail to climb high enough or fast enough, and who eventually concluded that some things simply cannot be caught. The State Route 71 Blackbird, the Habu, the world's fastest air-breathing aircraft, built from the metal of its adversary's Earth, powered by fuel that resisted burning, shaped by equations that had never been solved before, and flown by men who understood that they were doing something that would never quite be done again. 50 years after it first flew, engineers still study it. Aerospace students still write dissertations about its inlet system. Materials scientists still reference the titanium fabrication techniques developed for its construction. And pilots, even pilots who have never come close to flying anything like it, still look at photographs of the Blackbird and feel something that is difficult to name but impossible to deny. This is what it looks like when human beings reach their absolute limit and find that the limit is further than they thought. This is the State Route 71 Blackbird. This is the Habu. And it will never be forgotten because we will never, quite, be done understanding what it means that we built it at all. If you have found this story as remarkable as I have, if the story of the Habu has moved you, challenged you, or made you think differently about what human ingenuity can achieve, then please take 1 second right now and subscribe to this channel. Every subscription tells us that you want more stories like this one. Stories from the edges of human achievement. Stories about the people who refused to accept that impossible was a final answer. Hit that subscribe button, turn on the notification bell, and share this video with someone who loves aviation, engineering, or history, because stories this extraordinary deserve to be heard.